Hi there. I thought we would spend some time on the Unit 3 review so that we make sure we understand all the pieces and parts. Problem number one asks us to find the derivative at zero. And then we'll want to sketch a graph to make sure that what we're seeing on the graph lines up with what we're finding analytically. So if we take the derivative here, we're going to bring that power in front, making that 2/3 x to the negative 1/3. Let's rewrite this as 2 and then 3 to the cube root of x in the denominator. Now, if we're looking for f prime of 0, when we put in 0 for x, notice we end up with 0 in the denominator, which tells us that f prime of 0 does not exist. Now, when you put this in your calculator, take a look at the graph. You're going to find that there is a cusp there or a sharp turn. And that is why the derivative is not existing at 0. Okay, look at number 2 then. We want to find the value of f prime of 2. Okay, so I'm going to go ahead and rewrite that function as 4 minus 2x to the 1/2. So let's take the derivative. We'll pull the 1/2 in front. Decrease the power by 1, and then multiply by the derivative of the inside. The derivative of 4 minus 2x would be negative 2. So clean it up just a bit. Notice the 2 and the 1/2 will cancel, giving me just a negative 1 in the numerator. And then I've got a square root of 4 minus 2x in the denominator. So when I plug in 2, I've got negative 1 over square root of 4 minus 2 times 2. Again, I get this 0 in the denominator, which tells me that f prime of 2 does not exist. Now, when we graph it, we put it in our calculator, we take a look at what the graph looks like. We notice that it looks something, oh, forgive me. Let's do it the other way. It actually should be on this side, right? Okay. So why doesn't the derivative at 2 exist here? Well, the derivative at 2 doesn't exist because, I'm sorry, did I put that at 2? It should be, my graph's not wanting to work here. Should look something like that. Why doesn't the derivative at 2 exist? Because the function's not continuous at 2. The function exists, but the limit does not. And so therefore my derivative does not exist there. Okay, look at number 3 then. This is a good review of the formal definition as well as the alternate definition. So remember that the formal definition tells us that the derivative equals the limit as h approaches 0 of f of x plus h minus f of x all over h. You can easily see that letter A and B fall into this category. The trick here is to figure out what was the function. We're going to look at that minus the function here. And so on this one, I can easily see that the function is ln of x. And I know the derivative of ln of x is 1 over x. So instead of doing all the limits and everything, I can just pull out the function and then tell the derivative for it. All right, and then for b, let's see if we can pull out the function. It's sitting right here, so that'd be the cube root of 2x minus 3. I'm going to write it as 2x minus 3 to the 1/3. And then I'm going to take the derivative. So let's see. Pull the 1/3 in front for the power. Decrease it by 1, and then multiply by the power. I'm sorry, multiply by the derivative of the inside. The derivative of 2x is 2. So I've got a 2 coming to the numerator. I've got a 3 And I've got a 2x minus 3 to the 2/3 in the denominator. Okay, so again, that's just recognizing in the limit what the function is and then finding it in a little bit different way. Now, C and D follow the alternate definition of the derivative, which says that if you want to find the derivative at a point, let x approach that point, and then we have f of x minus f of a over x minus a. So the trick here is we've got to pull out the function again. Notice it's located in a different place. So when you're looking at C, you're going to pull out that the function is sine of x. But also pull out what is the question asking for? The question's asking for what is f prime of a? Well, a in this case is pi over 2. So the derivative of sine is cosine. And then we want to pull out, or we want to find the derivative at pi over 2. So we're doing cosine of pi over 2. Cosine of pi over 2 is at 90 degrees. Coordinates there are 0, 1. So the cosine is 0. Okay, let's do the same here for D. What is the function? The function is cosine. Okay, now look, D is in a little bit different format. Okay, D is more like this format, but notice that something has been plugged in for X. So it's still asking us, what is the derivative of pi over 4? But the function is the cosine, meaning f of x is still sitting here, but x has been subbed in. Pi over 4 has been subbed in for x. So let's find the derivative. The derivative of cosine is negative sine. And then we can find the derivative at pi over 4. Remember, pi over 4 is a 45-degree triangle. There it is. And across from the 45 is a 1, 1, and a square root of 2. So the sign here is 1 over square root of 2. Don't forget that it's negative. So I've got negative 1 over square root of 2, or negative square root of 2 over 2. Okay, let's look then at number 4 here. We're trying to find the equation of the normal line for this graph of y equals e to the 2x when the derivative is 2. Now remember, the equation of the normal line is perpendicular to the tangent. So easily in this question, you can eliminate C and E. And the reason is because the slopes in C and E are 2. That's equal to the derivative, not perpendicular. So we know that the tangent line is going to have the normal line is going to have a slope of negative 1/2. But what we don't know is what point that's going to happen at. So we're going to have to take the derivative and set it equal to 2. So the derivative here would be e to the 2x times the derivative of the inside, which is 2. And that needs to be set equal to 2. You can divide both sides by 2. That's going to give you 1 equals e to the 2x. Now, if you want to rewrite these to have the same base, you can rewrite 1 as e to the 0. So you get 2x equals 0, or x equals 0. So we know the point's going to be where x is 0, but what's the y value? So we take the function and we make x 0. That gives me e to the 0, which is 1. So we now know the point is at 1, 0. We have the slope of our normal line. We have our point. So let's write our equation of the normal line. So I've got y minus 1 equals negative 1/2 x minus 0. And that's going to end up giving me a here. Good practice, though, with the normal line, the tangent line, the slopes, and all of those good pieces. Really pay attention to those. I do apologize. My document camera kind of turned over here. There we go. All right, let's keep going with number 5 here. Given this function, what is the approximate value of 1.1 if you use the equation of the tangent line to the graph at x equals 1? So this one, I would start by writing the equation of the tangent line. So let's do the derivative. We're going to have to use a product rule here. So the derivative of x squared e to the x would be x squared times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of x squared, which is 2x. So we're going to end up with x squared e to the x plus 2x e to the x. And remember, this is when x is 1. So I've got e to the 1 plus 2e to the 1, which is 3e to the 1. That's my slope, okay? Now I need my point. So when x is 1, let's go back to the function. We'll plug in, I've got 1 squared times e to the 1, which is e to the 1. So my point is 1e to the first. Now here's what we're doing. We're going to write our tangent line. Let's do that. Y minus e equals 3e x minus 1. And now I want to plug in 1.1 for x. So I've got y minus e equals 3e, 1.1 minus 1. And that gives me y equals 0.3e plus e, because I moved this e to the other side. So friends, I'm going to end up with 1.3e. Now that's going to be a plug in my calculator and see what value I get for y. So I'm pulling up my calculator so I can type in this 1.31. Now, e is 2.7 something. So I'm really thinking I'm either going to be A or B. I'm not quite sure which one's going to turn out to be. But we will pull it up here. All right, and I'm going to type it in 1.3 times e to the first. And I got that 3.534 there in A. Okay, so what did we do there? We wrote the tangent line. When we wrote the tangent line, then we plugged in 1.1 for x to get our final answer. All right, look at 6. Now, I'm going to find the derivative at pi over 2. I've got a lot of chains going on here, so be really, really careful. My outside function is something being squared. So my derivative is going to be 5 times 2 times that something. Well, what was being squared? It was the cosine. Now, next chain is the cosine, so the derivative of that would be negative sine. And then the inside function pi minus x, the derivative would be negative 1. Okay. Try not to skip steps in there because it's going to cause you problems and going to miss some negatives. So I've got negative times negative is a positive. That gives me 10. Cosine of pi minus x, sine of pi minus x for my derivative. Then let's plug in pi over 2. That gives me 10 cosine pi minus pi over 2. Pi minus half a pi is half a pi. Sine of pi minus pi over 2. pi minus half a pi is pi over 2. Okay, so we're at 90 degrees, right? At 90 degrees, cosine is 0, sine is 1, so I end up with 0. All right. So far, so good. Good work with the derivatives here. Looking at number 7 then. For what values of k does this function have a normal line whose slope is negative 1/5? Now, friends, I remember normal line is perpendicular to the tangent. Okay, so if this is the normal line slope, what is the slope of the tangent? I'm going to flip it and change its sign. That means that my derivative, because that's the slope of the tangent, is going to be flipped and changed. So I'm looking for where is the derivative equal to 5, knowing that x is 1. So let's take the derivative of our function. K times derivative of e to the 2x is going to be e to the 2x times the derivative of 2x, which is 2, plus derivative of 3x is 3. Now we're going to set this equal to 5. And we're going to make x 1 at the same time. And now all we do is solve for k, right? So I'm going to move the 3 over. I'll divide by 2. And then I'm going to divide by e to the second. And I'm going to leave it like that. Now, if it's a calculator part and you want to put it in your calculator and get a decimal, totally fine with that. But you don't have to. You don't have to. All right, we're about halfway there. Let's take a look at number 8. Hopefully my document camera doesn't fall apart. There we go. All right, friends, very important. Make sure we know we are looking at the derivative graph. That's important. Because later on in the course, we'll be looking at the function or we'll be looking at the derivative. We'll be looking at the second derivative, and we want to make sure we're answering appropriately. So we want to make sure we know what we're looking at. Okay, so this derivative has a max or a min, has a max and a min, right? I know that the derivative is going to be some type of x cubed or x to the 5th graph. Okay, so what type of polynomial is the function going to be, right? Well, the function's going to have to be some type of quartic function. So I'm going to say f of x is a quartic function because f prime has 3 zeros. Do you see them? Look at the graph there. See the 3 x-intercepts? Those are the 3 zeros. That tells me the highest exponent in the derivative would have to be x cubed. Therefore, my function must be 1 exponent higher. Okay. 9 says, at what values of x does the function have horizontal tangents? So this is asking you, where is the derivative equal to 0? That's what it's really asking you. So it's going to be at those zeros. So we'll just say x equals -2, 1, and 3. And our reason, because remember it said to give a reason, because f prime equals 0. Voila. Be real exact. Okay, don't have to write a book on this one. Just give the analysis there. Okay. On what intervals of x would the function be increasing? So this is really asking you, where is f prime of x greater than 0? So look at where the derivative, those are the y values here, are positive. So I see y values, derivative values that are positive here, looking at the y values, and here. Okay, so I'm going to say from -2 to 1, think about why I use parentheses instead of brackets, because at -2, the derivative is not positive, it's actually 0. And then again from 3 to positive infinity. And again, give a reason, because f prime of x is positive. Okay, pause. Go ahead and pause the video. I want you to try 11. See if you can tell where the derivative, I'm sorry, where the function would be decreasing. Did you get it? Let's see. So the derivative, this is really asking, where is the derivative negative? Okay, so that's going to be from -infinity to -2. See, that's this section where these y values are negative. And then again in this section from 1 to 3. And why? Because the derivative is negative. Those are pretty good, all working from the graph, okay? No real calculus work to do other than analyzing, right? Analyzing the graph. We see these a lot in the free response. All right, look at number 12 then. Find two values on the interval from 0 to 2 where the slope of the tangent is equal to square root of 3. Slope of the tangent is code for derivative. So it's asking you find two values where the derivative of this would equal square root of 3. So let's take the derivative. Derivative of cosine would be negative sine, and the derivative of 2x would be 2. So I get -2 sine of 2x. And I want to know, where is that going to equal square root of 3? Well, let's go ahead and divide both sides by -2. And now we have to think about, where is sign negative? So maybe you learned all students take calculus to help you remember where the trig functions are positive. All are positive in quadrant 1. Sine is positive in quadrant 2. That means we're working in quadrant 3 and 4. All right. So I'm going to draw it in quadrant 3. If the sine is going to be square root of 3 over 2, I've got negative square root of 3 and 2 here for the sine being the opposite and the hypotenuse. That tells me that this must be a 60-degree reference angle. So to get all the way there, I've got to go 180 plus the 60. 180 plus 60 is going to be 240, which will be 4 pi over 3. Notice that I am setting this equal to 2x, since that is what is inside of the sign. We'll do the same thing in quadrant 4, right? Drawing our triangle, making the sign, noticing the reference angle. This time I've got to go 180, another 90, and then I've got to go 30 to get there. So that's going to be 300. I'll set 2x equal to 5 pi over 3. Now you can divide both sides by 2, or think of it by multiplying by 1/2 might be a little bit easier to give me 2 pi over 3 and 5 pi over 6. Now, friends, there are two more of them if you want to find them. You can take 2x equal to 4/3 pi and add a 2 pi to it. You'll find the second one this way. And do the same for this one. Now, the problem only asks for two of them. So all that I'm doing here is just totally extra. You don't have to do it, but I've had some students who ask about, how do I find those other two? And this is how you do it. And let's see, that's 10 pi over 3. And if I divide by 2, that's going to be 5 pi over 3. And this becomes 11 pi over 3. And if I divide by 2, that'll become 11 pi over 6. And there's 4 of them. Now, you only needed 2, but like I said, some students were asking about how do I find those other 2. So there you go. Okay, 2 more problems to go. Let's look at number 3 then. A good piecewise function. Wanting to know if A is -3 and B is 4, will it be continuous at 2? Well, let's put in those values for A and B. Let's see what we get. If A is -3 and B is 4, so now let's test each side. Now we know for continuous, the function has to exist. So we know that it exists. We can plug it into the first piece. I don't really need to know the value, but I just need to know that it does exist. And then let's test the limit because I think that's where we fail a lot. The limit as x approaches 2 from the left, we'll use the first piece. And then we'll set that equal to the limit as x approaches 2 from the right. And for that, we'll use the second piece. Now we'll plug in 2. Let's see what we get. 2 squared is 4 times 3 gives me -12. Oops, plus. 2 times 4 is 8 plus 2. And then over here, -3 times 2 gives me -6 plus 4. Let's see, I get -2 equals -2. So it looks like we are continuous because f of 2 exists and the limit as x approaches 2 of f of x exists. Okay, let's look at B. Now we're changing, will it be differentiable? Okay, so now let's take the derivative. F prime of x would be -6x plus 4 when x is less than 2, and -3 when x is greater than 2. Now I need to know if when I put in 2 from both sides, do I get the same value? So if I put 2 in here, I'm going to get -6 times 2, which is -12, plus 4 is -8, and that does not equal -3. Not differentiable at x equals 2 because the left and right derivatives are not equal. Okay, now C. For what values of A and B will f of x be continuous and differentiable? Okay, so we're going back to the original function. We're going to play off of that limit, right? The limit as x approaches 2 from the left, we use the first piece. And the limit as x approaches 2 from the right, we'll use the second piece. Now plug in 2. So x squared would be 4a plus 2b plus 2 equals 2a plus b. Now I'm going to move all the a's and b's to one side. So I've got 2a plus b, and then I'm going to move this 2 to the other side, and that'll be a -2. Okay, now let's do the derivative, right? So my derivative would be 2a x plus b when x is less than 2, and a when x is greater than 2. Now let's set these two pieces equal to each other when x is 2. So if x is 2, I get 4a plus b equals A. Again, moving all of the A's and B's to one side, I get 3A plus B equals 0. Now, I'm probably going to use elimination on this one. 2A plus B equals -2, and 3A plus B equals 0. Let's distribute a negative to this second equation. I'll get -A equals -2, or A is 2. Now we can use 3A plus B equals 0. We'll substitute 2 in for A, and I get that B is -6. So these are my values for A and B, that the function would be continuous and differentiable. All right, speeding along. We're on the last question, friends. This is a good one. Gonna need your calculator for this one for sure. You got a rodeo performer spins a lasso in a circle perpendicular to the ground. The height is given by this function. And we want to know, what is h of 0.75 and what does it mean? So this is where you're going to go with your calculator. I encourage you to put this function in y1. So you're going to put it in y1. Let's see, -3 cosine. Watch your parentheses with the 5 pi over 3. Variable. And then plus 5. Let me see if I can share my calculator screen with you here. Let's see, we're almost there. There we go. There's my calculator screen. So you can see what I typed in there. And once I get here, remember, you can graph with a zoom 6. It's not really good. The graph that we're after, we don't really care what the graph looks like. I'm more concerned about using some of the features after it's graphed. So this is how I put it in Y1. After it takes a minute to graph it, I'm going to use that second trace option. So I'm going second trace, and I want to do value for letter A. And notice at the bottom, I'm asked to type in 0.75 and enter. And the calculator tells me this is 7.121. Now remember, this is a function value. So look at your values, look at your units. The height from the ground of the knot measured in units of feet. So this is 7.121 feet. What does this represent? This is the height of the knot after 0.05 seconds. Now the 0.05, that was our t value, and it told me t was in the time measured in seconds. All right, now we want to find h prime of 0.75. All right, again, I'm using that second trace menu. This time, I'm choosing option number 6 for the derivative. And remember, I can use my cursor, but if I just start typing 0.75, did you notice the X showed up in at the bottom? And I can just type in my value, and it tells me that the derivative is -11.107. This is a slope. This is a rate. So this is feet per second. Okay, now explain what this represents. This is the rate of change of the height of the knot at t equals 0.75 seconds. So I hope that helps with the Unit 3 review. Be sure to post in the comments below if you have any questions. I'd be glad to answer those. Bye for now.